on this computer. And hopefully now when I share screen, yes, now I can see the slides. Um, why am I not shown here?
We can see your Zoom login at this point.
Okay, that's fine. I am trying to go back to the meeting and it won't let me. So what do we got here? New share. Pick up that. Share that. Can you see the slides?
Yeah, now we can.
Yes.
Okay, good. So, all right. So hopefully I'm also, yes, I'm also recording. So great. Oh no, that's share. What about the recording? Is the recording going on? No, yeah, it's going on. Okay, good. All right. I apologize. This is I have not used my Mac Mini in the past. I've always used my MacBook Pro, and unfortunately, it had some weird stuff going on. Anyway, so we're going to talk about general relativity, and I'm going to do a little bit of calculation in this one. I apologize for those who hate using mathematics, but I do want to show the difference between Newton's uh, gravity and Einstein's gravity and show that the two for regions around the Earth and the solar system are identical. So we're going to do a little bit of introduction and then we'll move on to Newton's laws of motion and we'll do his apple example. Then we'll talk about forces versus geometry. And then we'll wind up with Einstein's metric a la his 1916 paper. And we'll go through a couple of examples that are usually used, which are totally wrong. And then we'll use not curvature, but an effective scale, which you'll have seen in the previous material. I'm going to use a trick developed by Willem Killing to give me a simple example for Einstein's apple example. So, Einstein said a couple of things about time and space, and they're worth thinking about. Time and space are modes by which we think and not conditions in which we live. Um, that is thinking about the general ideas that Newton came up with are not actually the way in which we live, even though we're accustomed to thinking about it. A similar statement was time and space are not conditions of existence. Time and space are a model for thinking. So we're going through all of the same material we've talked about before. And I'm going to expand on the material that was given in the videos last time about forces and general relativity. and we're going to talk about the metric field about the surface of the Earth, and we'll use as the basic uh, way of thinking about this the fall of the apple from a tree that Newton's uh, realized was the same gravity as the moon. And we'll get not about curvature, but about the effects of time versus the effect of time in general relativity. I'm going to have to use the Schwarzschild metric to show that it's actually completely unneeded. Then we'll talk about Einstein's 1915 metric field, the one that he used showing the perihelion of Mercury, showed the orbits of the planets around the sun, did the calculation for light beam going close to the surface uh, of the sun, and all of these made the assumption that there was no curvature in space. We'll finally compare Newton's solution to the apple problem, and then after using a diversion of killing vectors, uh, we'll show Einstein's solution to the same problem. Okay, so we're going to be thinking about general relativity. So some questions ought to immediately pop up into your mind. What do you think some of these questions should be? They should be very similar to the ones we talked about in special relativity. So I'm actually not going to go to another app. I'm just going to start some of my own things. Does anybody want to ask any questions or any observe any what's the first thing that you would think of? I would say observers, same as there is in special relativity. Everything in general relativity, when you get to a small local region, reduces to Minkowski space. So the fact that in Minkowski space, every observer has a different, uh, their watch clicks differently, their meter sticks are different. The same thing is also true in general relativity. So if I'm in an inertial frame, what does that mean? It means I'm in free fall. I'm falling. I'm not being pushed by a chair. I'm falling straight down. Um, my watch is, if I'm in an inertial frame, just as in special relativity, my watch is ticking off proper time. My measuring stick measures distance. Another observer, if one is co-located, that is infinitesimally close and in the and not moving relative to me, velocity is zero relativity to me, then his watch will agree with mine and his measuring stick will agree with mine. But if he's not co-located, if he's got a different location and a velocity is non-zero relative to me, his watch and my watch will not agree, and his meter stick will not agree. Uh, his watch is different from mine, and his measuring stick is different from mine.
Bob,
Yeah.
when you make the statement, I'm in free fall, is this when you're in contact with the Earth, or if you're just somewhere here,
No, I
not in
have to
contact
either
with the Earth?
be fully away from all massive objects.
Okay, so you're in space. You're just, this
I'm
is
either in
just,
space or I have to be literally in free fall.
got it, got it. I
I,
understand.
I if you're sitting in a chair, you're not in an inertial frame.
Got it, because you're rotating continuously and accelerating continuously.
Right.
Got it.
Okay. So
Yeah,
some of the,
it's, if I just may interject a quick comment, to be in free fall, another way of thinking about it is to say you're in free fall when there are no non-gravitational forces being exerted on you. In other words, you could be in free fall if you're 10 meters above the Earth's surface, provided you're free from all non-gravitational forces. You'd be falling, of course.
right. You have to go up to your roof and jump off. And when you jump off,
You're in free fall,
you're in free fall.
right?
What does that mean, non-gravitational forces?
Well,
I
electric,
thought,
if you're sitting in a chair, then there's all these non-gravitational forces pushing up on your butt to keep you from falling down towards the center of the Earth. If you remove these non-gravitational forces, if somebody whisks the chair out from under you, for an instant, you'll be in free fall until you hit the floor. But that's when you hit the floor, that's another non-gravitational force acting on you.
well, what about the gravitational force acting on you?
No,
Well,
when you're
as-
in free fall, there's no gravitational. You're just floating. I mean,
as far-
you don't have any weight when you're free falling. That's the comet, the vomit comet. When you go in a parabola in a plane, when you go over the top, you start coming down, falling at the same rate as everything else. There's no gravitational force, none whatsoever. That's what an inertial frame in general relativity means. You have no gravitational forces, no other forces, no forces whatsoever on you. You're just freely falling.
Okay, the reason I brought this up is because Steve made a point of calling them non-gravitational forces, and you're saying any force,
well,
including
yeah,
gravitational force.
non-gravitational forces implies that there are gravitational forces if you read it that way, but it's non-gravitational forces means all forces due to interactions other than gravity. Gravity, as Bob will explain, looks like it's acting on you via a force, but that's deceptive. Again, as he'll explain, that's a manifestation of curvature in space-time.
Actually, almost entirely in time where we are
Right.
now,
Yeah.
not in space, which I'll go through.
Right.
Okay. So one of the things you ought to learn about is universality. There is a lot of things about physics that are due to universality. Steve, you want to do a quick discussion on universality?
I'm sorry, tell me again what what the context of this is.
Well, forces are, all of the laws of physics are basically universal. That is, if you have a law of physics that is true here, it's going to be also true in New York. It's going to be true in Alpha Centauri. It's going to be true in Andromeda. It's going to be in every place around the universe. So all of the laws of physics are universally true. You also need to worry about conservation laws. such as the law of conservation of energy, momentum, angular momentum, information, and a whole lot of other things as well. You should always ask, whose simultaneity are we dealing with? Who is the observer that we're talking about when we talk about simultaneity? Should I use a picture of a world map or world picture? Am I in an accelerated reference frame, rotation, or force of some kind? So these are all things that you need to think about. All right, we're going to move on to Newton's law of motion and gravity, which we've talked about a couple of times already. And Newton was the British physicist who formulated the laws of motion and gravity. The initial one, which turns out to be highly accurate for uh, small masses, but when, of course, there's much more large, massive objects around, then it no longer is accurate. So, um, Newton's laws hold only with respect to frames of reference called Newtonian or Galilean or inertial reference frames. And um, they are given interpretations of mass, acceleration, momentum, and most importantly for Newton, force, as opposed to being externally defined quantities. We're going to find that that's not actually uh, true. It was first superseded by special relativity and then also general relativity. So his first laws were that um, this, if the net forces on any object are zero, then the velocity of an object is constant. Second one said that the rate of change of momentum of a body is directly proportional to the force applied. The third was that any when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction. So masses, this is a measure of resistance to acceleration. So given uh, the two ponderable objects, as they were called, the force is proportional to the product of the masses for gravitational uh, forces. The force is oriented along the line of the objects, uh, along the centers, and inversely proportional to the square of the distance. And most objecting is non-locality. The forces are exerted on both objects simultaneously. So this is the picture. You have M1 and M2. The two forces are the same. They're G M1 times M2 divided by R squared, and they're directly from their centers. So this is the way it is. There is the constant G, which is Newton's gravitational constant, um, which is about 6.67 times 10 to the minus 11th meters cubed per kilogram second squared. So you can write it this way. The reason it's cubed is because you have a vector r at the top. So r over the magnitude of r gives you a unit vector in the direction of the r, the distance between the two. And you can, if you have uh, the masses essentially uh, constant, then you can determine a potential, which is G times M1 divided by R, or R vector divided by R squared.
Yeah, that you should really have that R vector as an absolute magnitude because the left-hand side's a scalar. And you need the
Oh,
right
you're right.
to
You're
be a
right.
scalar.
I shouldn't have done that. That's wrong. I apologize. Okay. So the gravitational fields are conservative. That is, the energy is conserved, momentum is conserved, angular momentum is conserved. So the work done by gravity is path independent. And the consequence is that you can have a gravitational potential and you can have an acceleration field, usually called for some reason a force field. I don't know why, since it's an acceleration field, but uh, the gradient of the potential is the acceleration. So Newton's apple, he was supposedly sitting behind a tree and noticed a apple falling. An apple is usually roughly 3 meters above the ground. So I choose the apple location in the tree as 0, and we see how fast it drops to the ground at 3 meters. So the potential can be written as a series about the radius of the Earth plus h, and the radius of the Earth is about 6.37 times a million meters. Um, when you take that and the mass of the Earth at roughly 6 times 10 to the 24th kilograms, you can do a series for the uh, potential in terms of the additional distance h. And if you stick the numbers in, you find that it's a constant plus 9.816, 9.82 meters per second squared, plus some small terms on the order of 10 to the minus 6. So we can ignore that and use the assumption that Galileo did, namely that the gravitational field is a constant. So the acceleration, h double dot, is a constant, 9.82 meters per second squared. The solution is minus 4.908 t squared. Same results that Galileo did using his marbles and inclined ramps. So Newton's apple directed to the center of the Earth. If you show the h as a function of time, it's a parabola. It starts at 0, drops down in about 8/10 of a second to minus 3, just accelerating faster and faster as it goes down.
Bob,
Yeah.
since you are recording this, there's audio coming in the background. Somebody's on the phone or something's happening, but you can continuously hear this audio right now.
Yeah, that's my wife doing yoga right now.
Okay, as long as it's in your end, that's all. I just wanted to let you know.
Yeah, sorry about that. I've got the door closed, but it still goes through the doors. All right. So now we're going to talk about forces versus geometry. So let's consider two pilots, Alberta Einstein and Isabella Newton.
Hmm.
And they both know that they want to fly from Perth to Durban. Perth is in Australia and Durban is in Africa, South Africa. And they're both located approximately the same latitude. So if we have a map here, um, we show two uh, pictures. One, Isabella decides, well, she has to go directly west. So she's going to take her compass, point it directly west, and fly directly west. Alberta will also go from Perth to Durban, but do it differently. So Isabella takes off in Perth, points directly west, and starts flying. As she flies due west, she's very surprised and upset. There's no crosswinds. She keeps her wings level, her tail straight, and yet she considerably flies southwest instead of west. Even her compass says she's headed due west. So she surmises that there must be a force pushing her to the south. In response, she has to consistently point northwest to compensate. Now, Alberta says, sorry, Isabella, you're wrong. You're flying on the surface of a sphere. There's no force, just geometry. My flight follows the shortest distance between 2 points on a sphere. And since we're both flying at the same speed, I'm going to get there before you do. See you when you get there. So Alberta, of course, is completely accurate. Her flight plan is a geodesic flight plan, a great circle on the globe going from Perth to Durban. Now, our map is Euclidean. It looks like it's flat. However, we know the sphere is not flat. So we can see how the scale of the map changes as our latitude goes lower and lower towards the south. This shows the map that we had previously. And what I've done is shown some lines of constant distance as we go south. So the distance between each line is about 1,700 kilometers. You can see that as you go down, the distance on the map gets wider and wider. And that's because of the fact that you're on the surface of a sphere. So the the change as you move along south of the distance being constant is different in the map. And you'll notice that Alberta's uh, flight plan is always orthogonal to these lines of constant separation. Isabella is not. And that's why Alberta's flight is shorter than Isabella's, even though it looks longer on the map. So I'm not going to teach about curvature, and I'm not going to teach geodesics, but I will use the scale change with time and space in general relativity to demonstrate that the usual pictures used to show general relativity are just completely wrong. I will, after I show that the time scale is millions of times larger than the space scale, and this is an example of change in space scale as you go around the globe. We're going to do the same thing around in general relativity. And I will show that using Einstein time variant of Minkowski space metric demonstrates the identical Apple results as Newton. And in the future videos, there's now 7 of the 8 general relativity videos that are coming up on the equations of general relativity. We'll discuss all of that. The third one is on geodesics, and we'll show the Newton's example using, again, but once we have geodesics under our belt, we'll be able to do the calculations more accurately. Okay, Einstein's metric in his 1916 paper. This is the usual picture that people get. By the way, are there any questions so far? Has all of this been easily understood? Anybody?
Oh, I'm not sure easily, but yes, it makes sense. It's quite interesting from a person who's always been in a Euclidean space.
Okay. Um, so the usual picture that people use is of a bowling ball on a trampoline. And then, they'll take a marble and have it go around the bowling ball as an orbit. But this picture is wrong. So why is this picture wrong? Can somebody, let me see, I'll pick a participant. Oh, let's see. Ernest.
I would venture to say that it is two-dimensional representing something that's three-dimensional.
No, that's not. I mean, that is certainly inaccurate, but that's not the main reason. I mean,
Well,
the one of the things that's inconsistent about it is that we're using gravity to demonstrate gravity.
We're placing the whole system in a gravitational field that's pointing downward.
right.
Okay, so that's inconsistent to begin with. So how could you use gravity to show the geometry of gravity? Now, although it's insistent, there's also another problem, and that is the symmetry of gravity. Gravity is spherically symmetrical. So if this were actually a accurate picture, you should be able to turn it upside down and it should work just as well. And it doesn't. If you turn it upside down, the bowling ball is going to fall out and the trampoline is going to be flat. So, I mean, it's just crazy. So, because Einstein's metric assumed that there was zero curvature, I'm forced to use the Schwarzschild metric initially to show that his metric was accurate. So the Schwarzschild metric is that proper time is c squared times 1 minus 2 over c squared times the Newton potential of R times dt squared minus 1 minus 2 times Newton's potential 1 to the inverse of that times dr squared. So the coefficients and terms of dr and dt are the scale of time and the scale of distance. They're the things that we were showing in the map of the Earth being flat.
This is a
So,
weak field approximation, isn't it?
well, I'm going to. This is actually the accurate. This is the Schwarzschild metric, and I'm just going to compute the terms from the scale. So the square root. Let's see, the square root of this and the square root of this are the
Okay.
changes of scale as you go in time or in distance. And I'm going to compute those square roots and um, show that the spatial part is essentially uh, zero and the time is all of the effect. Now, just an aside, in 1715, Isaac Newton and Gottfried Leibniz were heatedly debating whether the scale of distance and time really are the same everywhere. The debate was kindled by the Princess of Wales, Caroline, um, an extraordinary woman who was one of Leibniz's students. She realized that Leibniz's view of space and time was fundamentally different from Newton's. So she encouraged the two to exchange letters to resolve the issue. And Newton thought,
Bob,
yeah,
yep, could you go back to that equation you just, I don't mean to interrupt. This looks like what you've told us before is proper time. It's c squared times a delta t.
delta tau, yeah,
Okay,
that's proper time, right?
that's but before you define proper time with respect to something times a dt squared and then a dx squared, dy squared, dz squared. So
Well, I've
you've
got it here as dr squared. I'm using the spherical coordinates and I'm ignoring the angular portion.
because you're talking about the distance between the centers of two, or
Yeah,
it's one
I mean, you
dimensional.
you just makes it simpler to use that as a two-dimensional metric, uh, time and distance, and we're assumed that the distance is in the direction that you're falling.
Got it. Okay. All right. Thank
Okay, sure. Okay, so this is the Queen Consort of Great uh, Britain and the Ireland Electress Consort of Hanover, Caroline, picture on the right. And Newton thought it was obvious that the scale of space and time are everywhere the same, forming a fixed and immutable backdrop to the universe. But Leibniz thought that the size of an object only has meaning in comparison to other objects. And without a comparison, how do you know that the yardstick on the moon has the same length as a yardstick on the Earth, as an example? As Leibniz put it, these gentlemen, uh, there were two people. Newton didn't actually send the letters to uh, Leibniz, a proxy, Clark. Uh, he wrote the material, Clark sent them, and they went back and forth. So Leibniz said, these gentlemen maintain that space is a real, absolute being, but I held space to be something purely relative, as time is. Now, Newton's view uh, was definitely believed by everybody for the next 2 centuries. Rulers and clocks would seem to appear to be the same everywhere. And unfortunately, it was wrong. Leibniz turned out to be right. By the 1860s, Bernard Riemann had developed the mathematics of spaces, which the scale of distance varies from place to place. He noted that the geometry of the world around us is not decided by philosophy and debate, but instead is a matter for observation and experiment. So, going back to the Schwarzschild metric, the scale of distance, that is the 1 minus 2 over c squared phi of r to the minus 1, can be written as a series with a few terms. When you throw in the radius of the Earth, the velocity of uh, light, the mass of the Earth, and Newton's gravitational thing, you find out that it's approximately 1 minus 6.5 times 10 to the minus 16. And the next term is 10 to the minus 22. So you have to take a square root. When you do that and you do it numerically, it turns out to be essentially half of that term, that is 3.27 times 10 to the minus 16. So the change in scale of distance around the surface of the Earth is about 100 diameters of a proton. We can essentially ignore it. And that's what Einstein did. He assumed that it was 0. Now, the scale of time is almost the same, but it's not 1 over it. And it's got a c squared on it. So you can do the series again. And when you use the numbers, it turns out that when you subtract off the speed of light, the change in time is about 0.2 meters per second. Now, 0.2 meters compared to 100 diameters of a proton is about 100,000 billion times as much scale change for time compared to scale for change in space. And this is why all of the effects in general relativity around us are in terms of time.
Bob, could you define what this term scale of time means?
Well, the same as it meant for the change of space.
Okay, no, I can,
It's, you've got a metric, and in the one case, in the math that I was doing, the the metric is all about space. It's not about time. But in general relativity, the metric, just as it is in special relativity, mixes space and time. Proper time is a function of both. And so you can take a look at the change in space. And as we did the computation, it turned out to be about 100 proton diameters. But when we do the same calculation for the portion of the metric, so there's two terms in here.
Yeah, no, I understand that. I guess I'm just trying to, you're talking about then what are the contributions to the change in proper time?
Yes. Yes.
Okay, so between two observers in different places, there's going to be a change in proper time. And based on this analysis, that change in proper time is always due to change in time.
Yes.
Got it.
Right. Okay, so Einstein's metric with space being totally flat is quite accurate. The change in time scale for the Apple example is about 0.16 meters of time. And not surprisingly, that change is very small, but the total time fall is about 240,000 kilometers. So if the pictures of the fall of time, we would say it was essentially a straight line going down 240,000 kilometers versus a change of 3 meters. So I'm going to take a slight diversion and use killing vectors as a way to compute the Einstein solution to Newton's Apple problem. So I'm sorry, I'm going to have to talk a little bit about Willem killing and killing vectors. So Willem Carl Joseph Killing invented Lie algebras independently of Sophus Lie around 1880. Killing's university library did not contain the Scandinavian journal in which Lie's article appeared. Lie was later very scornful of Killing and claimed that all that was valid had already been proved by Lie, and all that was invalid was added by Killing. However, Killing's work was, although less rigorous logically than Lie's, he had much grander goals in terms of classification of groups and made a number of unproven conjectures that were later turned out to be true. So we're going to use one of the results he gave and use that to solve the Einstein version of Apple problem. So killing vectors are another way of using invariants. We keep coming back to this, and you should always be thinking, how can I use an invariant? So I'm not going to give a formal introduction to killing vectors, but you can consider using the two-dimensional metric we've been talking about. When you use the approximation that I had from before, if you essentially have -1 for the spatial portion and c squared minus 2 times 9.82 times the height. And that all of the Schwarzschild metric becomes this as an approximation. So the line element, which is the proper time, is the sum over the metric times dx mu times dx nu, summed over both x mu and nu, and that gives you this version. Now, if the metric coefficients g sub mu nu, not g mu nu, do not depend on any coordinate, say xk, then the particle for velocity, or in this case, to velocity, of the coordinate has to be a constant. This is the invariance of a killing vector. In other words, the scalar product of the for velocity on a vector psi is equal to delta. This is the delta is, if mu and k are identical, then you get a 1, otherwise you get a 0. And so the metric that we just showed shows that there's no time in the metric, only space, h. That's the only coordinate. So the killing vector in this case is a unit vector along time. And the result is that, oh, and another thing you have to remember is, if you remember from special relativity, we all go at the speed of light. Well, it's also true in general relativity. If you divide the metric by d tau squared, it also comes out to be the speed of light squared. So this is not just a result of special relativity, but also of general relativity. We all move at the speed of light. So using the killing vector, we say that the killing vector times the velocity vector, which you can write up here, is a constant. And you remember that the killing vector has a 1 for the time portion and a 0 for the space portion. So only the term here, the c squared minus 2 times 9.82 h times dt d tau and divided by c, is a constant. E is an invariant, that is a constant. As I said before, we also have another equation here. We have that the speed of light squared is equal to the magnitude of the velocity vector. So we have here c squared minus 2, 9.8 h, dt squared d tau squared minus dh d tau squared. These are the two equations we're going to use to solve Einstein's apple problem. I can compute dt d tau from the killing vector equation, substitute it into the equation for the velocity, and find out that we have dh d tau squared is one constant e squared over this minus c squared. So assuming at the initial velocity for h, I'm sorry, this is at h equals 0, we're doing the same place that we did in Newton, that is about 3 meters above the radius of the Earth. We're assuming that h is 0 and the initial velocity is 0. If you put that initial velocity in at 0 for h equals 0, you find that e squared equals c squared and e equals c. So now we can write d tau dt as just equal to this, but c squared is approximately 10 to the 17 compared with 19. So obviously this term is essentially negligible. So d tau equals dt. So, whoops, sorry. Where am I? I'm here. Okay. So that's one. Then this equation, I can approximate this as a series, and it gives you these two terms. I'm sorry, this is this one, yeah, dh d tau squared. This inverse of this is approximately 1 plus this, because this is so tiny. So taking the square roots, we have dh d tau, and using t is approximately tau, we get the equation dh dt is the square root of this, which is about 4.9, and times the square root of ht. And as we did before with Newton's equation, we set the initial velocity to 0 and h equal to 0. The solution of this equation, not surprisingly, gives the identical solution to Newton's gravity solution. We get minus 4.9 times t squared meters per second squared. So Einstein apple looks identical to Newton's, but using Einstein's 1916 metric, which had no spatial curvature whatsoever, the apple drops to the center of the Earth, accelerating at a constant rate. Now, all of these things have been true to approximately 10 to the minus 6. There are some about 10 to the minus 20th additional terms that are due to the rotation of the Earth, which we're not showing in this. I mean, there's a number of other things that occur in Einstein's results, but we're only using about 6 digits of accuracy in the computation we're doing here. And I would have to actually do the geodesics in order to give you all of those effects. But I hope that we've been able to understand that Einstein's 1960 metric field with no curvature of space whatsoever, only curvature of time, allows to give the exact same result as Newton. And we're going to do more material using the Click uh, Science Click videos. And the next 8 of those will describe the equations of general relativity. And when we get to the third one on geodesics, I'll do this example again using the full geodesics. So, questions?
It's a nice demonstration. Thank you.
You're welcome. Did everybody get a feeling for what was going on? Obviously, the computations, you have to do series, you have a whole bunch of things that are going on. But the end result shows that the curvature of time is what's important, not the curvature of space. So I hope everybody was at least somewhat able to follow what was going on.
Yeah, this was really quite interesting. I do have a question for you. What happens to the Earth during this? I mean, does where Newton had Earth and had this force that supposedly existed between the mass and between the two bodies. This general relativity deforms space and time relative to the two, but they both eventually end up at the same place. The apple ends up at the center of the Earth.
Well, yeah, and the Earth is actually also freely falling in the opposite direction.
Okay.
Just, I mean, the all of it is symmetric.
Yeah.
So the Earth is also in free fall. It's actually in free fall around the sun, not around the apple. But you can do the whole computation again, for this and show that the Earth going around the sun is exactly an effective time. Somebody else had a question?
Yeah, I wonder if there is a answer for that. If there is absolutely no curvature for either time or space, but would it be still holding that the photon velocity c is still the same and constant?
Yeah, I'm sorry, I didn't quite understand what the question was. Can you repeat it slowly?
Yeah, well, most of the information we have about the velocity of light is in space and time, which has gravitation present. Now, if there is no gravitation or any other force which would bend the space coordinates, let's say, and time coordinates, would that mean that also we have to assume that the velocity of light is constant?
Yes, well, it is. I mean,
How do we know?
well, the way the derivation of Einstein's general relativity equations, um, you have to assume, not
Yes.
assume, you show that as you get closer and closer, as you get to a smaller and smaller region, the all of the general relativity equations reduce to special relativity.
But even special relativity was assuming, because measurements had been proven that at our uh, ground on Earth, the velocity of light is constant regardless where do you measure it, what kind of coordinate system, and so on. But because we have gravitation present, would
Yeah,
that,
well, the assumption in general relativity is that when you get a small enough region, you're going to be in Minkowski space, and all of special relativity is accurate in general relativity. So the speed of the velocity of light has to be a constant, just as it is in special relativity.
I understand that the whole question about actually the special relativity was all the equations and all the assumptions were based on the velocity of light being constant. So that was assured by measurements made on the Earth. That was a good assumption. But what if you take away any kind of gravitational force? What would be then? Would that assumption be a good assumption? And can you rely most of the calculations on that?
Well, it is built into the equations of general relativity that the
Yeah,
speed of
it
light is a
is.
constant. And
Yes,
it is
on the
the,
assumption.
yeah. So just like any other postulate, what you have to do is look at the experimental results on the predictions of the equations.
But you
And
always have present something like gravitation, which could be not true all over space, or universe, I mean.
well, but that's not what we have observed. I
Well,
mean,
because
when
we
we
don't,
take a look at all of the results for, gravitational waves, black holes, the orbits of the planets, etc., everything, you know, turns out to give exactly the results that general relativity does.
well, exactly, because we are not able to get rid of the effect of the gravitation or other forces in our surroundings, let's say, whatever we can measure.
Well, but even when we do the calculations of what's going on in massive black holes and galaxies, the results are the same as those predicted by
Exactly, but
general.
they are also having gravitational present. If you
Yeah.
measure something in space where there is nothing, just maybe particles, maybe. And would that, maybe it's like not a good question, but possibly we could never really measure. But I was just thinking, everything is based on an assumption which we cannot say is generally true for the universe.
Well, yes, you don't know for sure that it is true, but
Exactly.
based on the assumption that it is, you make predictions.
Oh, I
And
agree.
every prediction we've ever made about general relativity turns out to be true.
I agree on that 100%. But what,
So that means that the postulates, which are the basis of general relativity, have to be at least closely accurate.
yeah,
Otherwise, the whole thing would fall apart. The predictions would be wrong. if the speed of light was not a constant, then general relativity wouldn't work.
And none of the other assumptions and theories either. So that part is okay. Whenever the world is, the universe, the same as it is now, and all these different galaxies exist as it is now, even if they move away from each other, but still they have some effect, I can believe it. But what if all these galaxies go way, way out and their possible gravitational or other forces are not possible to sense by any means? What happens then? Would that be holding as far as photons would exist, and would they just be running around with the same speed always? Or would they be, that wouldn't hold either?
Well, I couldn't understand what you just said. Steve, did you hear what she said, and can you answer it?
Well, if I understand Kathleen's objections, you're objecting to the assumption that the various constants of nature, like the speed of light, are the same everywhere. Is that correct?
Basically, because all those things what we have had assumed any value as constants or other, they
Well,
were
that's,
always
it's
holding for the
yeah.
case, which
Well, I'd have to look a little bit into that, but I know that there are an awful lot of phenomena, particularly in the region of spectral lines from distant objects, that if some of the constants of nature were not constant, these ratio of spectral lines would differ, and they don't. What I can't tell you right now is exactly what I know. It's one of the constants is the fine structure constant, which is a combination of some fundamental constants like the electric charge and the I think the Planck's constant. Um, but you can make observations like those, which indicate, well, I should say that nobody who has looked into this to try and see if the constants of nature varied over space, large regions of space or large periods of time, nobody has found anything that indicates that the constants of nature aren't truly constant.
Yeah, and in particular, if you take a look at all of the amount of different kinds of particles that were made in the Big Bang that created stars, all of that is based on the assumption that those constants were the same at the time of the Big Bang as they are now. And when we measure all of the concentrations of the various kinds of hydrogen and helium and lithium, all the rest of the stuff, we get exactly the results that are based on the assumption that they're constants. So, I mean, all of the experimental results that we've ever been able to check have shown that the constants of physics are the same in time and in space.
Yeah, I think people have looked pretty hard into that issue. And again, they haven't found any indication that the constants of nature aren't truly constants.
You're aware of that, aren't you, Kathleen?
what you mean?
You're aware of all of the results of the Big Bang, all of the measurements that we've done in various parts of the universe, everything is based on the assumption that the constants are identical every place in
Yes.
space and every place in time.
Of
And
course.
every experiment we've ever done, it shows the same results as
Yeah,
what
I
is
agree
predicted.
I agree on that. Whatever so far has been observed has not been not justifying this assumption. Now, if let's say if the universe is expanding and it expands very quick, fast, that was the actual measurement data coming from assuming that the velocity of light is constant, for example. But if they get far enough from each other, so far that in between the space would not, there would not be any kind of remains of any kind of forces like gravitation. And if that measurement could be done somehow, that the speed of light is the same through that completely forceless space is the same, then I would say there is just an interesting possibility to believe that, yes, it is constant for whatever the conditions are, gravitation or forces around or not.
Well, the basis of physics is experimental results. So
Yeah.
if you think that they're not the same anywhere, you have to make some predictions about what you would view differently,
That's
then
a
go
good
do
point.
the experiment and find out whether or not it's true.
Well, that's
I
a
mean,
very good point.
that's the whole basis of physics.
But maybe is that possible to see from the spectral distribution change of very distant galaxies?
Well, they've looked at that and haven't found anything.
What should that be different? Well, like if there is a difference in velocity of light generally, of photons, would they differ for different colors, for example?
Yeah, the ratios of various frequencies for um, different changes in, the hydrogen atom, helium, all of the others. If you start taking a look at the ratios of these things, if they weren't constant, they'd get different results than we get when we go measure it. That's
That would be exciting.
and we've tried, and we've never found anything different than the assumption that the speed of light is a constant. In fact, all of all of the gravitational constant, the Planck's constant, the electric charge, every measurement has shown that they're all the same every place in the universe and over time.
Yeah, this is, I understand all this, and this is very good so far. I only object to say, because we haven't seen it yet, that it is absolutely must be true for cases what we haven't even seen and possibly imagined. I would be happy to say that the
Well,
speed of
that's
light,
always true. I mean, that's why we keep looking with more and more, uh, you know, particle accelerators. We do cosmology. We do all of this stuff because we keep looking to see whether or not that any of the equations we have, any of the assumptions we have are wrong.
good.
And
That's
that's the reason you keep looking, and why there are hundreds of versions of general relativity. The Taylor, the vector scalar tensor version, etc. Every one of, there's hundreds of versions of general relativity that people have tried. Some of them have different constants. Some of them have varying speeds. There's a whole bunch of stuff that people have tried, and they've all been wrong.
Yes, anyway, I don't want to go very far with that discussion because there is no solution. I would be only meaning that I believe all those constants are true, but it should be always understood within the limits of our knowledge at this time.
Well, that's always true. I mean,
Yeah, but it's not
that's-
said. It's not said so in most places.
well, there's tons of people who have tried to do, versions of general relativity that didn't have the speed of light a constant. They were all thrown out because of experimental results.
Yeah. Okay.
So, if you can come up with a new version that has the velocity of light changing, make the predictions, go do the observation and find out whether or not you're right. That's the way science works.
Okay, I promise I will do it as soon as I put that to the part of the universe where there is absolutely no gravitation. I will do it, I promise.
Okay. Any other questions?
Thanks as always. Very interesting.
Okay. Well, I'm going to, let's see, I'm going to stop the recording.